Jay gave you the overall view of the project, and I'm responsible for the combustor aspects, combustor design aspects, and I'll just give you a brief overview of the challenges that we have and some insights into our approach. So, as you know, we all rely on aviation, and aviation is pretty much responsible for me coming to America, and some of you able to go around the world. These engines that are used on airplanes, they're very complex technology, and it goes through actually a new engine design. It's billions of dollars spent in doing that, and that's why. And the technological hurdles are tremendous, and that's why you don't have many companies developing engines in the world. You only have like a handful of companies with the know-how how to make these engines. Next time when you fly, you see this kind of rotating blades, and if you look outside of your plane window, you will see that there's things rotating, right? So these are rotating turbo machinery, and here is a cutaway of that one such engine. So this presentation, I'm mixing it so that I know some people don't have an idea of what engine looks like, and so I've kind of mixed the details with the simple elementary stuff. So please excuse me if some of these are things that you already know. So what is rotating is you have these compressors that compress the air. You want the air to be at a sufficient density, so you have to compress them, and then it enters the combustion chamber where it mixes with fuel, because that's where the energy is coming from, and then part of that energy is extracted by the turbine to power the electricity, right? So you need avionics, and you need air condition and lighting and all of that. But most of the remaining hot gases are expanded through the nozzle to produce that forward power that we need to move the airplane. So if you look at a cutaway of an engine, you see that air is going through the series of you only see the first blade when you look at the engine, but you see this air going through a series of compressors, and it enters the combustion chamber and expanded through the nozzle. So these sections are really hot. These are combustion conditions. So typically, temperatures that can melt metals, right? So the design and development is very complex. Anything that flies, it's not just a question of whether it works. It needs to work reliably, because people's lives are at stake. You may not want to get into a plane where that okay, it's a new engine that has not gone through sufficient validation, right? So it's a very complex technology, and here is a similar there are different types of engines. This is called a turbojet engine, this is a turbofan engine, but at the core of all of these engines is the combustor, where you mix fuel with air and then burn, right? So what is traditionally done is to use fossil-based fuels. So jet fuel that we currently use. So Jay mentioned Jet A and few other fuels. Those are all hydrocarbon-based. So hydrocarbon means hydrogen and carbon, right? So when you burn hydrogen, produces water. When you burn carbon, produces CO2. We don't need CO2 because that's what we are trying to eliminate. And so what is our idea? We mix hydrogen and ammonia, and we think that a combination of hydrogen and ammonia will have equivalent performance, combustion performance, compared to an actual hydrocarbon fuel. So you can see some numbers here. For example, the flame speed. This is basically how fast the flame will propagate in a combustible mixture. it's around 37 centimeter per second for a traditional hydrocarbon fuel, whereas for hydrogen, this is 291, almost 10 orders of magnitude, right? Whereas for ammonia, it's slow. So a combination of these can meet that number. And so from a design point, hydrogen ammonia combination can make sense. And there are other properties that I have listed here. And so that is basically what we are trying to do. We don't know exactly what combination will make sense, and it needs to work for the entire range of operation of an airplane, from takeoff. The conditions inside the engine are different than when you are cruising and when you are landing and so on. Now, you cannot just burn anything and worry only about the performance. You also have to worry about other things that goes on as a byproduct. So this is a high-level overview of what happens inside an engine to a fuel, right? So traditionally, you have this fuel mixing with air, and these time scales show what happens to that fuel. And a microsecond, 1 millionth of a second, or 1,000ths of a second, there are things that break down the fuel, and there are species that form, and some of those species end up in the tailpipe at the back end. So CO, CO2, water are traditional products, but then you also produce NOx. NOx is a nitrogen oxide. This is a pollutant that is regulated, and we don't want to produce NOx, but unfortunately it exists. So you have to minimize it to meet the requirement. So in order to understand this process, we have to develop several models, and we also have to do experiments to validate the model, right? Any model without experimental validation is junk. Unfortunately, there are other complexities that exist when you design an engine. You do want the flame to stay there, and you have that sustained, I understand this is a very busy slide. So you do want to have a sustained flame so that, you produce a propulsive power, right? You don't want to get into an airplane where you know that the flame can go out, right? I mean, on land, if it's your car or truck, it's okay. You can stop on the side of the road and, restart the car. But for an aircraft engine, that's not the case. If the flame goes out, then, things crash, right? So there are issues while burning new fuels. So the flame can go out, or it can actually creep in towards the injectors. And so there's a lot of fundamental properties of these mixtures that decide the actual behavior inside a combustor. And we have the facilities and tools to obtain this knowledge. As you know, I do I'm mainly an experimentalist, and we have several facilities on campus. Some of you might have heard of shock tubes, and we have a new world-class facility called Hyperstar that's shown here. This is a very unique facility in the world, which has been funded by the College of Engineering. And this is a unique facility. It can access a wide variety of conditions that exist inside a real engine or rocket engine or aircraft engine, whatever it is, right? So for this project, we'll be also constructing new experimental facilities to study the aircraft combustion. Now, there is a funny thing about ammonia. Ammonia, I showed you the series of what happens to the fuel, and ammonia breaks down and eventually produces NO. This is the unwanted thing. We don't want NO, right? But this NO or NOx can react with ammonia and go back to being nitrogen. So what happens is that there is even though ammonia produces NOx, ammonia can be used to control NOx. So this gives us opportunity to meet, minimize NO or even meet zero NO, and which is what the world wants. So we have started looking into taking some preliminary data and trying to understand ammonia hydrogen system. So here are some of the example data and model development that I've been carrying out in my group, and we will be taking more relevant data for this project. One thing that I mentioned, developing a new engine is very difficult. And one of the approaches that industry follows is what's called reactor network modeling. So what happens is that this is your engine, and if you look at the combustor, right, it has this kind of geometry. So you have the main air coming in, and then here is the fuel that's being injected, and then fuel mixes with the air and burns here, and then by this point it's mostly products, and then you expand that through the turbine, right? So this is a very complex thing to model. And if you remember, computer-based tools are used for almost every design these days. But the first jet engines came out in the 1950s, and when computers did not really contribute to that design, right? So they used this approach called reactor network modeling at that point to develop those engines. And primarily, it is like this: you have this big engine, and let's section that into different zones, based on some of these are based on measurements. So you can measure temperature at different points and see, okay, now I'm putting one zone here, two zones here, and so on. And the whole overall goal of this approach is to model that engine and figure out what comes out at the end, and what are the engine sizing, what should be the size of this combustor, what's the length of the combustor, and so on, right? So we can gain a lot by doing this kind of approach. And we'll be collaborating with the GE, which is the largest engine maker in the world. And so we are very excited about that. So we will be working with them closely to, they have their own in-house models, but they will be relying on us to provide the experimental data. And as I said, every model without validation is junk, right? So we'll be doing that as part of this project. And as I said, ammonia can be used for NOx control. And so in this project, we plan on converting some of the ammonia into hydrogen. May not be 100% conversion to hydrogen. Maybe there's a right combination of ammonia hydrogen mixtures that is suitable. We don't know what is that combination at this point. And we'll be mixing that with air in the combustor, and then we'll be injecting ammonia to control basically NOx. And so you'll also get further heat release here. So this is the overall approach that we are pursuing. And I have not given you a lot of details about the individual tasks or the efforts that we have. But if you have any interest, you can always reach out to me, and I'll be happy to provide that. So this project has not come in like overnight to us. We have been fortunate enough to get funding from different agencies over the years. And at Cater, we have several collaborations with a lot of industry and government agencies, and all of these have helped us to obtain this project. And I'm also very thankful to my students. So this is a picture from our mini golf in 2021, and we recently did a natural hike. Hike in Florida. You have to put that in quotation, right? So, but still, there are some nice places close to UCF where you can do the hike. And I'm also very thankful to the chair, the dean, and vice president of research, and also the staff who help support these proposals and award. And they do that, and takes helps me to focus more on the research aspects. So at this point, I welcome any questions.